Okay, so these are the do now questions that we had today. I'm going to go the extra step of actually solving for it. So doing the solution. So I'm going to go the extra step of actually solving for it. But in today's do now, all we were asked for you to provide was the type of limit and then the method of evaluation. So really quickly, I'm going to go through each of these problems. So how I'm going to solve this first problem, right? I would like for everyone to copy this down if they haven't yet already for their do now. So I'm going to give 10 seconds to copy this problem down in their notebook. Awesome. So the first thing we want to look at is we're going to look at where x is going to, right? X is going to -5. And we notice that it's going from the left. But first, let's just try to directly plug in -5. So when we plug in -5, right, we're going to put in 2x. Well, I'll write this over here, actually. 2 minus x. Yeah, so -5 goes in for x, and then -5 plus 5. Well, then we're going to get a 0 over here, right? Yeah, thanks, Clea. So basically, again, anytime we have a 0 in the denominator, just in math in general, like in the field of math, basically. So basically what happens then when we have a 0 in the denominator is we know that there's no solution, and that tells us that there's an asymptote there. So an asymptote occurs, again, let's say there's an asymptote at this dotted line, and then a function approaches it, and it never actually reaches the asymptote. And you'll notice this is where that 0 is occurring. So it would be occurring at, well, in this case, it'd be occurring at -5. So it'd be occurring like over here at -5. So you'll notice the lines never actually touch -5. There's no solution at -5. So this, because there's a 0 in the denominator, right, when we plug in -5, and also we can't simplify it, right? We can't factor it. Factoring is not possible. We know that this is an asymptote limit. Basically, when there's a 0 in the denominator, we're going to know that it's an asymptote limit. And also we have to make sure we can't like simplify it or algebraically manipulate it like factoring or anything like that. And we can't do that here. So we know this is the asymptote limit. And then the way we solve asymptote limits is we plug in values that are very close to the asymptote, but not quite at the asymptote. So we're coming from the left here, right? So we're going to plug in a number that's slightly less than -5. And it's very close to -5, but it's not going to be -5. So let's plug in, let's say, -5.1, right? So let's do that. And then we plug in x equals -5.1. We're going to get 2 minus -5.1, right? We're just plugging it in for x. -5.1 plus 5 is equal to 2 plus 5.1 is 7.1. -5.1 plus 5 is -0.1. I'm going to do quick math and show that it's -71. And then when it's negative, we know it's heading down to -infinity. This number could be like -1,000, -40. We don't really care. All that we can see is that it's negative, so we know it's going down. So the answer is -infinity. And just to visually show what that might look like again, is that at this asymptote, right, at -5, we plugged in a number really close to -5, right? We plugged in a number here, and it was very negative. So what's probably happening is this, right? Because it's going way down. If we wanted to find what was happening over here, we could plug in a number. It might be positive, it might be negative. If it was positive, it would look like this. If it was a negative number, it would look like this. So yeah, that is just a rough picture of how to do that problem. I will give 15 seconds to copy down anything that you might want in your notebook. Well, I expect the work in your notebook, like the graphs, these examples and stuff, they don't really have to be in your notebook, but it could help. So I'll give another 15 seconds for that. And yes, I would like, someone asked me privately, yes, I would like this to be in your notes. Again, like I draw like little graphs for visualization sometimes, and you don't necessarily have to have everything, but just like the general problem and how you solve it, I would like for that to be in your notes. And this applies for future problems as well. And again, I am recording these lectures, so I'm going to start posting them regularly. If you miss any of this stuff and you want to turn in notes that are complete, you can just skip to the lecture like after class ends. Should be uploaded a few hours after class. Okay, so I'm going to move on to the second problem now. And when we look at this limit, I would say before we do anything, the first thing we should notice that it's going to infinity. This automatically tells us that it's an end behavior limit. Any limit that's going to infinity or negative infinity, infinity, or negative infinity, that tells us it's an end behavior limit. Now, how do we solve end behavior limits? We solve end behavior limits through the hierarchy of dominance that we learned. And basically with the hierarchy of dominance, we remember our first step is to isolate dominant terms. So the dominant term in the numerator is x to the fifth, right? It's more dominant than x squared. So I'm going to circle x to the fifth, but I have to remember that what also matters, signs matter. I'll say it that way. So hierarchy of dominance, also don't forget that signs matter. So this negative right in front of x to the fifth matters because that's part of the x to the fifth term. In the denominator, it's pretty easy to tell, x squared is the dominant term. So we're going to circle x squared. This negative is part of the 12x term, right? So I'm not going to circle this negative. It doesn't really matter. If the negative was over here, then I would circle it, just to make that clear. Okay, so now I'm going to rewrite the limit. So in the solution, I'm going to rewrite the limit as limit of x to infinity. Actually, I didn't give time for everyone to copy down the problem, so I'll give like 10 seconds right now so people can catch up. Awesome. So the limit is x is approaching infinity with, I rewrote the limit, so it's negative x to the fifth in the numerator, right? We just forget about everything else. For end behavior limits, all we care about are the dominant terms, right? So we literally, these do not matter. So negative x to the fifth over x squared, right? So now we're evaluating which is more dominant. So is it the top or the bottom that's more dominant? We can see that x to the fifth is more dominant than x squared, right? So we're going to say the top is large and the bottom is very small, right? Because as it goes to infinity, x to the fifth increases much faster than x squared. And then now we have to look at the signs. That's the second thing. So we first do look at dominance. Again, dominance, hierarchy of dominance. Then we look at signs. And the sign tells us that it's negative. So this is going to infinity. The sign tells us, sorry, this is going to infinity. Sign tells us that it's negative. So the answer is negative infinity. So the limit as x approaches infinity, the whole answer for this is negative infinity. So again, for end behavior limits, we use hierarchy of dominance, and then remember that signs also matter. I'm going to give 15 seconds for people to copy this down. And just try to really understand what we're looking at when we're going to infinity. Again, we're paying attention to the dominant terms. And then also for like negative infinity, this is a really minor thing, but like, remember how we did negative infinity? And then if negative infinity goes into is raised to the fifth power, it's going to be negative, right? And then there's a negative here, so that's actually positive. So if this was going to negative infinity, the numerator would actually be positive. So it's very important to pay attention to the signs and really think about what the signs mean. Luckily, this is x going to infinity, so it's very easy. All we have is this one negative sign, so figuring out the signs is very easy. Cool, so another 10 seconds for this. Awesome. Okay, so now we're going to move on to the main topic of today's class, which is continuity. And first, we're going to look at it graphically. So this is the main topic of today's class. I will say you don't have to copy this graph in your notes right now. This is mainly for you to look at. What we're going to do right now is I'm going to give everyone 2 minutes to privately just like write down in your notebook, looking at this graph, what the casual definition of continuity is in your mind. And then we're going to come together as a class to come up with a casual definition. So there is a mathematical definition that we can precisely define continuity with mathematical terms. But right now we're just looking at it like if you were to try to explain to someone what continuity looks like, what do you think it would look like? So you can use this graph as reference. This graph specifies that it is continuous here, but it is not continuous at -2 or -1. So again, 2 minutes, please begin now and come up with your own casual definition of continuity. So just to clarify, to make sure everyone understands, Jay, would you be able to come off mute and clarify what we're supposed to be doing right now?
We're just going to be looking at the graph, and we're going to come up with our own casual definition of continuity.
Awesome. Thank you for that. And yeah, that's exactly right. So yeah, 2 minutes. Thank you for that. Maybe 45 more seconds, and then, okay, thank you, Marsha, for already sharing. If once you finish, if you just want to type in your name into the chat, and then I'm gonna call on a volunteer just to share, maybe 1 or 2 volunteers just to share what their definition is. Okay, so that's around 2 minutes. Marche, please come off mute and share what the definition you came up
I
with.
said a function, a continuity is even a function. Nah. Sorry.
No worries, no worries. Take your time.
Was a function. I gotta show my phone up. So I said a function is when a continuity is when a. All right, hold on again, real quick. Sorry, hold on.
No worries, take your time.
So I was saying a function is when, or continuity is when a function will keep going through points on the graph without having to have any gaps or issues. So like at -1, it's a jump continuity, and at 2, it's also a jump continuity as well, or discontinuity, my fault. So anywhere where the graph is just like keep going without any stops, it's a good graph. It's continuity. It's continuous, my fault.
Awesome. Yeah, so that's a great way of putting it. So you said if the graph like continues, probably shouldn't use, I don't remember specifically what you said, but continues without any gaps or issues.
Yeah.
Awesome. Yeah, so that's a great way to put it. I'm going to simplify this for us and try to make it even more simple. I'm sure some of you guys remember this rule of thumb, but if you can draw and this is the function, this is the definition that we'll use as a class for our casual definition. If you can draw the function without picking up your pencil, then it is continuous. So I'm going to give everyone 10 seconds to write that down. And I'm going to demonstrate that really quick. So we already clarified that at -2 and -1, they're not continuous, and at C it is continuous. So I'll start with, at 3 it is continuous. So at 3, I can just very clearly demonstrate I'm following this function, right? I'm going to take my marker, follow it, and then draw through C, and then it's totally fine. I didn't have to pick up my pencil, nothing. I can draw through it, and it's continuous. Now at 2, I notice as I draw here, but there's a hole, and the hole is there's like the actual point is located at 2, whereas the function is at 4. So I would have to draw here, pick up my pen, make a point here, then continue drawing. And because I picked up my pen, that means it's not continuous. At -1, it's even more obvious. At -1, I'm drawing here, and I have to make a huge jump down here. Because that's not what the graph shows. So yeah. Hopefully you guys were able to see that. It says my internet connection is unstable, but hopefully you guys were able to see that. Basically, again, if you can draw the function without picking up your pencil, then it is continuous. Okay, so now I'm going to try to refresh everyone's memory on the formal definition of continuity. And this is the definition that you guys really have to remember and understand all the elements of, because it's a definition that they're going to test on the AP test. The casual definition can be helpful just so we can kind of visualize and understand continuity. But whenever we need to prove it, or whenever like the AP test asks you continuity. So for something to be continuous, we, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 41, 42, 43, 44, 45, 46, 47, 48, 49, 50, 51, 52, 53, 54, 55, 56, 57, 58, 59, 60, 61, 62, 63, 64, 65, 66, 67, 68, 69, 70, 71, 72, 73, 74, 75, 76, 77, 78, 79, 80, 81, 82, 83, 84, 85, 86, 87, 88, 89, 90, 91, 92, 93, 94, 95, 96, 97, 98, 99, 100, 101, 102, 103, 104, 105, 106, 107, 108, 109, 110, 111, 112, 113, 114, 115, 116, 117, 118, 119, 120, So I would like for everyone to write this down, this definition, and then once I finish writing it down, I will prompt everyone to show their notes in the camera. So in the screen, so please make sure you're diligently writing down this definition of continuity. So first, the first element is that f of a must exist. So I'm going to give everyone 5 seconds to write that down. And just to clarify what that means, to say f of a must exist, for example here, let's say this point didn't exist and there's just a hole in the graph, then we know it's not continuous because I would have to pick up my pen and basically jump over that hole and then continue drawing. So the point must exist. So the function must exist, essentially. F of a must exist. The second element is that the limit as x approaches a of f of x must exist. I'm going to give everyone 5 seconds to copy that down and really think about what that means. So when we're saying that the limit as x approaches a of f of x must exist, what we're really trying to attack the idea is that the two-sided limit. Yeah, Marsha, thanks for participating. That's exactly right. So the two-sided limit must exist. So this attacks, sorry, I'll finish this. Give 5 seconds to copy that down. All right, thank you for letting me know, Ashley. Okay, so the two-sided limit must exist. So this attacks this discontinuity, right? So for a two-sided limit to exist, they have to come to the same point. So they have to equal each other. For example, this limit approaching -1 is going to 1. This limit is going to -3. Because they're different, right? They're not the same, -1 and -1 and -3. We can say that this two-sided limit does not exist. So obviously this point at -1 fails our second criteria for continuity. And our third criteria is that it's kind of combining them all together. So this is the actual full definition. So the limit of f of x as x approaches a, so this same exact thing right here, must equal this point right here, f of a. So this right here is our actual definition for continuity. So we can circle that because this kind of combines the first two steps. I'm going to give everyone 15 seconds to write all that down, and then please hold up your notebooks in the camera just so I can see that everyone's copying down the notes. Thank you, Charles. Thank you, everyone, for who's already doing that. Awesome, awesome. Thank you for everyone who did that. I did see your notebooks. And again, if you aren't in a camera frame, please return to the camera frame and hold up your notes. And also, if you have your cameras off and you haven't messaged me yet, please remember just to message me or have your cameras on. Awesome, thank you, Jamal. Thank you, everyone. If you've been holding up your notes, you can probably put them down. I'm not going to read everyone's name, but thank you to everyone who is doing that and following directions. Okay, so just to clarify this third point, right? I'm going to go back to. So the third point is that the two-sided limit must equal f of a. And going back to this, the first discontinuity at -2 again, we're kind of attacking this discontinuity again. Remember for our first one, we had to use an example where this point didn't even exist. Well, even if this point exists, we have a two-sided limit that like works, right? They're going to the same point. So technically, the second requirement is fulfilled. F of A also does exist. So that's fulfilled. But the issue is that the two-sided limit does not equal F of A. The two-sided limit is going to 4, right? It's going to 4. F of A is at 2. So the issue here is that they're not equal to each other. You don't have to write that down. I was just illustrating the point how this third, right? So this third requirement actually matters. Saying that they're equal to each other actually is significant. Again, because even though this two-sided limit exists, and even though F of A also exists, they have to equal each other. So this point right here has to move up to here. Or this function could be like that also. But yeah. Great, thank you for everyone for taking the notes. Now we are going to, with the time that we have left, I'm gonna minimize this. Okay, so I'm gonna give everyone 5 minutes or so to essentially utilize, like apply our formal definition of continuity and explain why each of these examples doesn't fit with that definition. So each of these are discontinuities, which means that it violates our definition over here somehow, right? It violates somehow. Actually, I'm going to give everyone 1 minute right now just to kind of copy the graphs. You don't have to like copy every element of the graphs, but just like kind of represent what each of these graphs looks like. And then under that, I'm going to give 5 minutes for everyone to express in our like actual mathematical definition why it's not continuous. So first I'm going to count down for 1 minute, just so everyone can get the graphs in their notes. Give 30 more seconds. It may be helpful to remember these terms, removable, jump, and infinite discontinuity, although I don't think they're the most important things, especially for the AP exam and stuff. It's more important to like understand them mathematically than like know the names, but it might be helpful. Okay, I'll give maybe 15 more seconds, just in case people are writing this down. Notice with the infinite discontinuity that there's an asymptote here. This is an asymptote, so if this helps you understand limits. Yeah. Okay, cool. So before we move on to this second activity, I'm just going to fill this part in, the casual definition. Basically, well, basically we can't draw f of x without picking up our pen. Yeah, so I mean, this is kind of just easy because it applies to the whole thing. I just wanted to express for each of these, again, like here, I have to pick it up to draw this dot and then move on. For the jump one, I obviously have to pick up my pen. For the infinite discontinuity, it's even more obvious. I draw up here, it keeps on going up, so I would have to pick up my pen to go down and draw the other part. So it obviously violates our casual definition for continuity. But I would like for everyone now to take maybe 4 minutes now to see if they can express why each of these graphs violates the formal definition for continuity. So please take 4 minutes to start that now. 4 minutes. And once you complete that, please chat your name into the chat. So start that now. Thanks. About 2.5 minutes left, and just to make it easier, if I want to look at their notes, but this is the definition. For continuity, again, I'll just write it out. So I'm going to give just a bit less than 1 minute just for the sake of time. Awesome. Okay, so Tibert, would you be able to come off mute? Also correct me on the pronunciation of your name, because I don't think I've called on you before. And then you can take us through your thought process for each one.
It's Tavere.
Tibert, awesome.
And the first one, I said that that f of a and f of x as x approaches a don't equal each other.
Yeah, awesome. So I'll clarify that really quick. So I'm gonna show each one of these like in terms of the definition. So the limit of f of x as x approaches a, the two-sided limit does exist, right? Like they're both going to the same point. So that's a check. F of a also does exist, right? We can see it up here. So that's also a check. But the issue is that they're not equal to each other. Notice that they're going to different points. The limit's going to this point, and f of a is way up over here. So they're not equal to each other. So it fails this third and final point. This is our third requirement. So thank you for that. And then how about the second, jump discontinuity?
The jump discontinuity, I said that the limit of f of x as a approaches, I mean, as x approaches a doesn't exist.
Awesome. Yeah, that's exactly right. So when I write out this definition again, it's this first requirement. The limit of f of x as x approaches a. Well, for this to even like be part of the equation, it must exist, right? But we know it doesn't exist because they're going to different points. The limit approaches that point from the right and a different point from the left. So it fails this first requirement. Once it fails any of them, we don't even have to look at the rest. We know it's not continuous. Cool. How about the third, infinite discontinuity?
The last one, it doesn't match up any of the quote unquote rules that we have for it. Like the limit, it doesn't exist because one, you could see that on the left side it goes up to infinity, but on the right side it goes down to negative infinity. F of a doesn't exist, and obviously they're not going to equal each other if they don't exist.
Yeah, that's actually, wait, that is a great response, because if you think about it, this infinite discontinuity, it literally fails every test. So if you think about it, the limit is going way up, this limit is going way down. So obviously the limit does not exist. F of a, there's an asymptote here. We already showed how asymptotes, like, there's no point that exists here. So F of a does not exist. And obviously if these two things don't exist, they can't possibly equal to each other. They don't even exist. So it fails all three tests. So thank you for that. That was a great response. Make sure you have all these notes copied down. There's 2 minutes left at the end of class, so take like 1 minute to copy this down. And then after you copy it down, you're free to go. Remember to, again, have the exit ticket done, turn in your notes for today by 10 p.m., exit at 10 p.m., and then get started on the homework packet that was assigned over the weekend that is due Thursday night. I will be posting videos, hopefully before too late tonight, like of me working through example problems that are going to be very similar to the homework packet. So look out for that if you intend on working the homework packet tonight. If not, you can always have Wednesday and Thursday to work on it. So yes, thank you for that. And have a great rest of your day, and I'll see everyone in class tomorrow. Thanks, Kayla. And then I'll stay after class for a couple minutes if anyone has any questions. Bye, Clarissa. Hi, Jay. Yeah, what's up?
All right, so I'm gonna exit it right now and just determine whether f of x is continuous at each x value. Justify all answers using formal limit notation. And yes, actually work on. Wait.
Wait, sorry. Sorry, could you clarify that question again? The last part. Your audio is kind of
I was
like hard.
wondering,
Mhm.
X would be equal to 1 because, well, I'm trying to find it. Wait, hold on.
All right, take your time.
So,
Did you have a question at x equals 1 or?
I'm just a little confused because I see that there's 1, 1, and there's 1, 2 at an open circle.
Yeah.
So is
so if you were to
like
if you were to use our casual definition, right, where like we're looking if we have to pick it up, would you say it's continuous or not? If we were just looking at it like casually, I guess.
No, because you have to pick it up.
Yeah, awesome. So then we know that it's not continuous. So in terms of our formal like limit definition, one part must not work, at least, right?
Yeah.
So looking at the first part, does the two-sided limit exist? Like, does the function go to the same point?
No, it doesn't, because 1 is an open circle and 1 is a closed circle. So it's a jump discontinuity.
Yeah, it's close. So you're right that they don't equal to they're not equal to each other. It's a removable discontinuity. So I'll clarify, like, wait, if you're looking at my screen, right, it's kind of it's the same deal as this. So the two-sided limit actually does exist, right? Because the function is going to the same point from the left and the right, right? They're both headed here, right? And also, the point f of a does exist because it is defined. The issue is that they're not equal to each other. So it's the exact same issue as here, because they're both going to this point. F of a is up here. So there's obviously a difference. Does that make sense?
Yeah. Wait, so that means for 1, that means for x equals 1/2, then okay. That means x equals 1/2. Wait.
Are you looking at x equals 1.5?
Yeah.
Yeah, so that one, I would say, like, if you look at it casually, right, at 1.5, you can kind of just draw a line through it. So it doesn't seem like it violates our casual definition of continuity.
Because 1.5 isn't the 1.5 y equals 2x?
Yeah, it's that part. So it's between 1 and 2. So if you look between 1 and 2, it fits right on that like straight line that's going down.
Yeah.
but it's right in the middle of that line. And if you look at it, like you can kind of tell there's no clear discontinuity there, right? There's no hole, there's no jump, there's no asymptote, so it would be continuous.
Okay. So
And then,
in our casual definition, it would be continuous. So,
yeah, so that means it also works with our formal definition. Our formal definition, basically all the requirements are met. So it fits. And then you just have to kind of show that in your work. I mean, basically you could write it down and write down the formal definition and kind of write down that it like works. Also, I do have a class this next period, so I'm gonna have to move on to the next Zoom call. No worries, yeah, I can usually take a couple minutes, but thank you for asking questions. If you have any more, just email me. It's just I have to get going.
all right. Thank you.
But, yep, see ya.